Implicit differentiation can be tricky. In fact, I think it's probably the most requested topic on my channel. It's tricky for a few reasons, but it can be even harder when you have to start combining it with other derivative methods and tricks, like chain rule, for example. So in this video, I'm going to be showing you an example of how to solve an implicit differentiation problem by solving for dy dx in a problem that requires the use of chain rule and also product rule. It's kind of a lot to keep track of, so I really wanted to break it down and make it as simple for you as possible. So by the end of this video, you should be feeling a bit more comfortable with implicit differentiation combined with other methods of taking derivatives. If that sounds good, be sure to stick around to the end of the video. And without further ado, let's go ahead and jump into the problem and I'll show you what I'm talking about. Find dy dx by implicit differentiation, where this time our equation that we have is y to the fifth plus x squared times y cubed equals 1 plus y times e to the x squared. So this equation is quite a bit more complex than the first example we went into. I am going to go through it a little bit quicker just because I went into quite a bit more detail about, function and variable and all that stuff going over the first example. If you want to go back and rewatch that, feel free to do so. Real quick, I'm just going to kind of point out, again, we have y is our function. So whenever we have a term that has y in it, we have to be sure to treat that as a function of x, and x is our variable. So let's go ahead and get into how we actually take the derivative of both sides of this equation with respect to x. So first, we'll just go term by term. Basically, whenever you have pluses or minuses, you split it up there, basically. So in this case, we have one term here, one term here, one term here, and one term here. So first term, y to the fifth. Again, we have to do chain rule here because y is a function of x. We cannot just use the power rule here. We have to treat y as our inside function and then the fifth power portion as our outside function. So chain rule says that the derivative of one function plugged into another function, like we have here, is going to be the derivative of the outside function. So the derivative of the fifth power piece, we'll bring the 5 down in front, leave our inside function as our inside function, leave our y as y, and then subtract 1 from the power. And then we multiply by the derivative of our inside function. The derivative of y with respect to x is just dy dx. Now this next term here, we're going to have to actually use the product rule. So product rule says that we take, basically, let's actually kind of make like a little side problem out of this. We'll say this is one of our functions, this is our other function. So these two things are being multiplied together here. So we'll say, basically, x squared is f and then y cubed is g. So then we need to find y prime, or f prime, I'm sorry, and g prime. So f prime, derivative of x squared with respect to x, that's just power rule. You bring the 2 down in front, keep the x as x, lower the power by 1, 2 minus 1 is 1. The derivative of y cubed, very similar to how we just did this one over here, we're going to bring our 3 down in front, leave our inside function as our inside function, lower the power by 1, and then multiply by the derivative of our inside function, which is y, which is dy dx. So that was kind of a mixture of product rule and chain rule kind of combined into one thing to find this derivative. So then what we need to do is we do f times g prime. So we do x squared times 3y squared dy dx. And then g times f prime, so 2x times y cubed. So now this is the derivative of this whole term right here, x squared times y cubed. Okay, and then on the other side of our equation, we have a constant. So we have equals, the derivative of a constant is always 0, so that's just going to be 0. And then to find the derivative of this term here, let's go ahead and kind of break that up into a few pieces as well. Because again, we're going to have product rule and chain rule required to find the derivative here. Because we have the product of these two pieces here, right? So y is one piece and e to the x squared is one piece. Let's just call that f and that g. We need to then find f prime and g prime. So now this is the prior piece. We'll keep that separate. So f prime is just the derivative of your f, which the derivative of y with respect to x is dy dx. Okay, And then g prime is the derivative of this piece here, e to the x squared. Well, e to the x squared is kind of interesting because it actually requires the use of the chain rule twice. We have to use chain rule twice to find the derivative of e to the x squared, because we have basically an innermost function, and then kind of like a medium inner function, and then an outermost function. Actually, sorry, that's not quite right. Nope, we do not have to do that. I'm sorry, I'm overcomplicating it. Okay, so e to the x squared is just going to require chain rule once. We're having to use chain rule within the product rule here, so it's really not too different from what we had to do here. If instead of e to the x squared we had e to the y squared, we would have to use chain rule twice, because y would be an innermost function within itself. Since we have x squared though, what we can do is we can treat x squared as our inner function, and then the exponential function as our outer function. So we would take the derivative of the outer function, leave the inside function alone, while the derivative of the exponential function, e to the x, is just e to the x. So the derivative of e to the x squared, if we're leaving our inside function alone, just taking the derivative of the outside function, we still have e to the x squared, okay? And then what we have to do is multiply that by the derivative of the inside function, the derivative of x squared. The derivative of x squared is just 2x. So that's going to be our g prime. So now for this overall derivative of this whole thing here using the product rule, we're going to get f times g prime. So y times e to the x squared times 2x plus g times f prime. So e to the x squared times dy dx. So now we have taken the derivative of both sides of our equation with respect to x. So now, same process that we always want to go through with these implicit differentiation problems. Once you've taken the derivative of both sides of your equation with respect to whatever your variable is, in this case, since we had dx on the bottom, we knew it was x. Once you do that, you want to move all of your dy dx terms to one side of the equation, all of your non-dy dx terms to the other side, and then we can go from there. So let's just mark real quick. Our dy dx terms are right here, right here, right here, okay? So those are going to need to be on one side of our equation, and our non-dy dx terms are here and here. Here we have a plus 0. That doesn't really do anything, so we'll just get rid of that. So we need to move this term over to that side of the equation, and then we need to move this term over to the other side of the equation, to the left side. So first thing we will do is minus 2xy cubed from both sides. Okay, and then we will minus e to the x squared times dy dx from both sides. Whoops, that's supposed to be an e right there, sorry. Okay, so that will cancel with that. This will cancel with this. So what we will be left with at that point, we're going to have a 5y to the 4th dy dx plus 3x squared y squared dy dx minus e to the x squared dy dx. And that's everything on the left side. And then on the right side, we're going to have 2xy e to the x squared and minus 2xy cubed. Okay, and I think that should account for all of our terms here. So once you've gotten all your dy dx terms on one side of your equation and all of your non-dy dx terms on the other side, from there what you want to do is factor out the dy dx from all of your terms that have the dy dx on that one side of the equation. So we're going to basically factor out dy dx from all three of these terms on the left side. So if we take the dy dx out of this term, we'll be left with 5y to the 4th. If we take the dy dx out of this term, we will be left with plus 3x squared y squared. And then if we take the dy dx out of this term, we'll be left with minus e to the x squared. Okay, the non-dy dx side of the equation is not going to be impacted by that because all we've done is factor something out of one side of our equation. And the reason we wanted to do that is now look what happens. Look at where we are at this step here. This is kind of the whole point of wanting to move all our dy dx terms to one side of the equation. And again, that is always what you want to try and do when you're doing an implicit differentiation problem. Because now, notice something very interesting about this step of the process. there's only a single dy dx term left in this equation. There's no other ones anywhere else in our equation. Basically what we've done is we've consolidated all of our dy dx terms down into one single dy dx. And the reason why that's so nice is if you have dy dx times a bunch of stuff, and that's the entire left side of your equation, what can you do to get the dy dx all by itself so that it's solved for? You can simply divide both sides of your equation by all the stuff within the brackets here. And then that will cancel. I'm not going to write that all out again, but that will cancel with this whole thing here. And then you'll just be left with dy dx equals everything on the right side of your equation all over everything that was within the brackets here. And then that's going to be it. We've solved for our dy dx at that point. And like I said, that's exactly how these implicit differentiation problems are almost always. I don't like to ever say always because you never know what you might get, but almost always going to go. Like that's going to be the strategy that you want to try and apply because it's really going to help you a lot. It's going to make things so much easier for you 99% of the time. Well, I hope you got some value out of that video. If you did, do me a favor and hit that subscribe button and that bell icon down below. And hit that like button while you're down there too. It really helps my channel get spread out to more people so I can keep making more videos like this. And if you subscribe, I'll help you keep on crushing it all term long in calculus. So we both win. Anyway, if you want to keep learning about implicit differentiation, just go ahead and click on one of those videos over there, and I'll see you next time. Thanks.